So we are recording this test 3 review written work topics, and we'll get started here in a couple minutes. It is 7 p.m. and I'm going to start on time. So what I will be going over today is the test 3 written work required topics. There are 7 of these ALEKS topics. They will appear in the first seven questions of test 3. I do want to mention that I'm going to assume that you have read and understood the contents of all Canvas announcements, especially those that have to do with testing. So I encourage you all to read or reread those announcements very shortly before you take test 3, so you are familiar with the contents of all of them. So there are testing violations that were determined by our department/division. So be sure you know those. It's very important that you get a clear picture of your government issued ID. There is one special announcement just devoted to getting a clear picture of your government issued photo ID. So please have a look at those announcements. I will assume that you have and know the contents of them. It is your responsibility. That was stated in the syllabus at the beginning of the semester. It's the chief way I have to communicate with you is through Canvas. So let's get started on the written work required topics. I am doing these topics in a different order than they will likely be in the test, but the 7 written work topics will definitely be the first 7 questions of your test. That way you know which ones to upload to Canvas, and it's designed to be as simple for you as possible. So I'm going to go down to my desktop to take a look at these written work topics. Here are the written work required topics. Let's start off with this one, expanding a logarithmic expression, problem type 1. This may not be the first of the 7 questions. It may be 2, 3, 4, 5, 6, or 7. So what we want to do here is use the properties of logarithms to expand log of the argument x over y squared. So what I want to do is I want to put parentheses around this argument, like that. So every logarithm consists of 3 parts: in log, in a base, which could be understood, and an argument. All 3 parts together, for any x and y in this case, represent one real number. So you can't, log is not a number, so you can't divide both sides by the log or anything like that. So, and the base is understood to be 10 in this case because it's log, and when there's no base stated and it's log, it's understood to be base 10. So we can't divide or multiply both sides by base 10. So you really need to keep all 3 parts together. So we have some properties of logarithms, and they are logarithm of a product, logarithm of a quotient, and logarithm of a power. These rules are named for what's going on in the argument. So we have log base A of the argument mn. What's going on in the argument is that we have an understood multiplication symbol between m and n, so we have a product. So the logarithm of a product rule states that the log base A of a product is the log base A of the first factor, which is m, plus the log base A of the second factor, n. Right here, the logarithm of a quotient states that the log base A of m divided by n, we've got a quotient in the argument here, that is equal to the log base A of the numerator minus the log base A of the denominator, n. And we have the all-important logarithm of a power property, which says that if you have log base A of a base m to a power p, then what you can do is take that power and drop it down front in the normal line of writing, and then not write it down again. So this power gets dropped down in front, and then you write down log base A of m. The power went down front, so we don't put it in the exponent. Speaking of exponent, every logarithm is an exponent. A log is an exponent. That's what it represents. A special note, these properties will not be given on the test. So what do we need to take a look at here? We want to expand a logarithm. That means write it as more than one logarithm. So here we are looking at log of x divided by y squared. So I'm going to put parentheses around the argument. Like that. So as I mentioned, these properties are named for what's going on in the argument. Do you have a product, a quotient, or a base to a power? And here we have a quotient in the argument. So we are going to use the logarithm of a quotient rule. And what does that state? It states that if you have the log base A of m over n, a quotient, that you can expand the log by writing down the log base A of the numerator minus the log base A of the denominator. So let's do that. And just to as a reminder, this is really log understood base 10. So we could have a base 10 written down here, like so. I could squeeze in a base 10. I just squeeze it in here, base 10. Let's see. We'll just squeeze in the base 10 here. And let me get in a 0 there. So we're talking about log base 10 of x divided by y squared. So the log of a quotient is the log of the numerator minus the log of the denominator. So we have the log of the numerator is log of x in the normal line of writing, and we've got understood base 10 down here because it's log. So it's log base 10 of x, in other words, log base 10 of the numerator minus log base 10 of the denominator, which is y squared, log base 10 of y squared. Now we're not done yet. We're not done until we make sure we've used all the rules that we can here. So what we want to notice is in this particular term here, we have in the argument y squared. We have a base to a power. We have a logarithm of a power rule that tells us what to do if we have has our argument. In other words, our entire argument can be written as a base to a power, which ours can't. It's base y raised to the power 2. So what does this property say? This property says that we can take this power, what's in the power, also you could say what's in the exponent, and drop it down front down on the normal line of writing. And then drop it off, or you won't. Once you write that P out in front, you don't write it down again. You're only going to have that P out in front. So that P stands for power. So we want to bring this 2 down front. And when we bring this 2 down front, this power down front, we write it as a 2 in front of the log, just like that. 2 log of what? Every log needs a understood base or a base and an argument. So we definitely need an argument in there. So we bring the 2 down front, then we get log base 10 of y, and that's it, because that exponent of 2 went down front. So this is what we get. Hello, I see you there. So let me know if you have any questions at any time. I've just started presenting the first written work topic. So I am recording this session, and I will make the recording available to all students in both of my online ALEKS classes. So I'm going to close off the side here. So we just looked at a written work required topic, expanding a logarithmic expression, problem type 1. You will see these 7 required written work topics. They will be the first 7 questions of your exam. We're not necessarily seeing them in order here, though. I will tell you that each one will be one of the first 7 questions, though. So let's go on. Let's look at this topic, solving an exponential equation by finding common bases, linear exponents. So I wrote down a property of exponents here that we are going to use. What happens if you've got a base raised to a power and all of that is raised to another power? Could be the same power, actually. And what we do if we have a power raised to a power, we write down the base and we multiply those exponents together. But we have to make sure we can write it in this form where we have parentheses around the b to the power. And then all of that is raised to a power. So what we're going to attempt to do here is to get like bases. This 64 is actually the base of an understood exponent of 1. And this 32 is the base of the exponent x minus 1. We want to see what we can do with those bases. And what our objective is to get matching bases. So let's start with 32. And let's break it down. So 32 is even. It is divisible by 2. And if you take 32 and divide it by 2, you will get 16. 16 is even and is divisible by 2. So 16 is 2 times 8. And you could get that by taking 16 divided by 2 and also get the 8. And 8 is even, so we can divide it by 2. And if we do that, 8 divided by 2 is 4. 4 is even, so we can divide that by 2. 4 divided by 2 is 2. So I circled all of those 2's. 2, 2, 2, 2, and 2, we have 1, 2, 3, 4, 5 2's. So that means that we can write this 32 as 5, well, 2, actually 2, I'm thinking of the exponent at there, to the 5th. So 32 is equal to 2 to the 5th. This 5, this exponent is mathematician's way of telling how many of the base do you want multiplied together. And that means, this 5 means we want 5 2's multiplied together. 1, 2, 3, 4, 5. Now our other base on the other side over here is 64. And what we notice is 64 is even. Therefore, it's divisible by 2. And if you take 64 divided by 2, you will get 32. You will get the number that we have here. So we can stop now because we know how many 2's multiply together to give us 32. That's 5. 5 2's multiplied together give us 32. And we have, for 64, we have one additional 2 right here. One additional 2. So now for 64, we can write that as 2, not to the 5th because we have one additional 2, but 2 to the 6th. And feel free to ask questions at any time. I'm going to leave the slide out in case I want to mark up something. So we take out this 64 here, and we replace it by 2 to the 6th on the left side. Close this off. And then this 32, we replace by 2 to the 5th. And put it in parentheses. And then we are going to need to raise that to this exponent, x minus 1. So what do we have here? If you notice right here on this side, this looks a lot like this rule that for exponents that we talked about, where you've got a base to a power, got a base to a power here, parentheses around it, and that's raised to a power. All of this base, the entire base here, 2 to the 5th, is raised to a power x minus 1. So our m is 5, and our n on the outside is x minus 1. And what does this power raised to a power rule tell us? It tells us that we can write down our base, and then we multiply these exponents together. There's an understood multiplication symbol there. So we want to take this 5 and multiply it times the x minus 1. And I wrote that like this. 2 raised to the 5 times x minus 1. And what we have now is we have a base of 2 here that's at the bottom of the exponent, 6. And we have a base of 2 here that's at the bottom of the exponent, 5 times x minus 1. When we have like bases, we can equate the exponents. That is, we can make the exponents equal to solve the problem. So our exponents are 6, and then this 5x minus 1. And we can make those equal to each other. 6 equals 5 times x minus 1. So let's solve this for x. Let's distribute this 5 through. We've got multiplication over adding a negative, so we really have multiplication over addition, so we can distribute 5 times x, and then 5 times a negative 1. Let's write the minus sign down like that, and then do 5 times 1, and we get 5 here. To solve for x, let's undo subtraction by 5. The opposite is adding 5 to both sides. So we get 6 plus 5, which is 11. On this side equals minus 5 plus 5 is 0, plus 5x is 5x. And lastly, we need to divide this both sides by 5 to get x by itself. So we divide this side by 5. So we have 5x, and we're dividing this side by 5. And then we also want to divide 11 by 5. And then The 5s cancel. Actually, it's good to know why they cancel. 5 divided by 5 is 1, and 1 times what's left is what's left, which is x. So we get x equals 11/5. Now you might wonder, why on earth does that work, or does it even work? Let's see. Let's check. Yeah, I think it'd be a good idea if we check this. It's always good to check, especially on a test. And let me see if I can find some room to check. So our original equation is 64 equals 32 here. And I want to check. I'm going to move that up just a little bit. And I will write down 64 to remember how to use my markup tools. These are freebies that come with software, so they're actually pretty good. 64 on this side equals 32. This is our original equation. 32 x to the minus 1. And we think that x is 11/5. So that's what we would be putting in for x up here. 11/5. So if we do that, we're going to still have 64 on this side equals 32 raised to 11/5 minus 1. Well, I'm going to go get the graphing calculator, and I'm going to combine these and math frac. I'll show that to you in a second. So this is 11/5 minus 1. So I have a graphing calculator here. It's actually an emulator, and I will show you how to do that if you don't already know. So I'm going to go to the home screen. That's this quit up here, and that is in blue, so I need to use my blue second button. And so that's actually second mode, and that's going to take me to the home screen. So I'm going to type in 11 division 5 minus sign minus 1. And I want to convert it to a fraction in lowest form. And the way I can do this is I can go to this math key right here, click on math. It's in the first column there. And you will see that the 1 is highlighted in black, and it looks like, hey, that might change it to a fraction. And that's exactly what it does. And the way you can do this quickly is to do enter, enter. So it's math, enter, enter to convert to a fraction. So we've done the math. Let's do the enter key twice. And you see I get that we get 6/5 over to the side here. So this is equal to 6/5. This is very handy to have. So what we have up here in the exponent now is 6/5. So we have 64 equals 32 to the 6/5. So now let's go back to the calculator and check this side to see if it truly is equal to, let me just check that, 6/5, yeah. We want to see if 32 raised to the 6/5 power is indeed 64. So I'm going to write that down. We've got 32 to the 6/5. Let's go back to the calculator. So this time we want to write down, type in 32, 3, 2, and we want to raise that to the 6/5 power. This little mountain peak right here, this will raise to any power you want. I use it all the time rather than looking for where I find us to square a function, or where if I'm looking to cube a number or take it to the 4th power or take the square root or whatever, I usually always just use the mountain peak. And so I'm going to click on that mountain peak and it will give me a box to put an exponent in. So I want to do 6 division and then 5, just double checking, and then enter. And what do we get? We get 64. So I'm confident that we got the correct X. So I know that I've showed my detailed written work and I've got the correct answer. So I should get a high score, probably get 7 points for this problem on the exam. So let's go back, and at any time, feel free to ask questions. So let's go on. So let's take a look at solving an equation involving logarithms on both sides, problem type 1. The very first concept I want to mention is it's really vital that you check to make sure whatever you get for your possible solutions, you check those to make sure all arguments must be positive. It is impossible to take the log of a negative argument, and it's also impossible to take the log of 0. I can show that to you on the calculator. The log button. This is log base, this log is log base 10. This ln is log base e, really. If I push on this log and I try to take the log of 0, and apparently I can use some of the keys on my keyboard, like the 0. So I'm trying to take the log of 0 and I hit enter. Error domain. Value entered is not allowed in the function. There's an issue. So that suggests that you can't take the log of 0, and that is absolutely 100% correct. You cannot take the log of 0. And next, let me go back to the home screen by doing a mode. Actually, I have to do the second first and then the mode. There we go. Let's take the log of a negative number. So we go and use this one this time. Since that's log base e there, let's put in -5. So negatives in the bottom row of the calculator, right here, a negative, and 5. And close that off. And hit enter. Error, now non-real answers. So I do this to hopefully so you remember that you cannot take the log of a negative number and you cannot take the log of 0. So let's go back. And this is really important. Arguments are what you're taking the log of. Examples of arguments in this equation are x minus 3 is an argument. All logs have an log, or understood log, have an log. You could say an ln, but an ln is really log base e. So all really they have a log, all have an log if you look at it in the right way. Every log has an log, a base in this case. This 4 is down off the normal line of writing, and an argument. The argument here is in parentheses, and it is x minus 3. The 7 and 2 are there because I was checking in the argument to make sure that all arguments are positive. And if I didn't get a positive argument, I threw it out, threw out the number that I thought could be a possible solution. And over here, we have log base 4 of the argument x minus 6. So x minus 3 is an argument, and x minus 6 is an argument. That's what you're taking the log of. And both this x minus 3 and this x minus 6 must be positive. When you solve for x, you're going to get x, but you still have to subtract 3 from it to see if that is positive. And then you will also need to take your x that you get and subtract 6 from to see if that is positive. So let's go down here and take a look. So I copied the problem down. I'm just double checking. I copied the problem down here. So we have properties of logs that if we want to get our logs on the same side, because sometimes we can use either the product property or the quotient property of logarithms. So let's add, the opposite of subtraction is adding. Let's add log base 4 of x minus 6 to both sides. So I wrote it down here and here. So on the left side, we are going to have log base 4 of x minus 3 right there, plus log base 4 of x minus 6 equals this one. This is minus the same number as we have plus of, so that's 0. And 1 plus 0 is 1. So that's what we have. It's preferable, it's easier to solve logarithmic equations if you can write as a single log. So what we have here is the sum of this log and that log. So we have a property of logarithms that we call the product property that says if you have the log base b of a product, that's just the sum of the logs. But we can also use this property in the other direction. We can use this property in this direction. So if we have the sum of 2 logs, we can write that as a single log of the product. Now, what is in the product? What's in the product is this in the first log is this argument x, and in the second log is this argument y. And when we're combining into a single log, notice what goes in this argument here. What goes in this argument is the argument of the first log x and the argument of the second log y, and they are multiplied together. So in our example here, when we combine these logs, we've got a plus sign in between, which is required to use this property. We're going to write as a single log, and both the logs have to have the same base to do this. So both of our logs do, so we're going to write log base 4 down off the normal line of writing a little bit, and we're going to take this argument and this argument and multiply them together. So we have x minus 3 has an argument and x minus 6 has an argument, and we have them multiplied together. There's an understood multiplication symbol here, and that equals what's on the right side, which is 1. So we are going to now convert this log to an exponential equation to solve it. And the way we do this is we start with the base. A single log is an exponent. A log is an exponent. So we're going to get the exponent next. exponent. Okay, so we've got the log as an exponent. And then what's left? So then I'm going to write down what's left. This is the way I usually think about it. I'm not a big fan of lots of notation. What is left? Although we can't eliminate it altogether. What's left? That's the question. There we go. So as mentioned before, a log has 3 pieces. It's got the log, it's got this base. So this is the base of the logarithm, that's 4 here. This inside the brackets is the argument. And then we have this one on the other side. This entire left side is a log. A log is just an exponent. And this log is equal to an exponent of 1. So we are going to convert to an exponential equation. You could look at it that way. It has an exponent over here. So we're going to take the base first and start. The base is 4. I'm going to write down our base 4. Now it's the base of a power, so it's on the normal line of writing. Well, every base needs an exponent if we're talking about an exponential equation. And our exponent, remember the entire log is an exponent? So and that exponent is 1. So our exponent is 1. What's left that needs to be written down is this argument. What's inside here? X, and we write that down on the other side. That equals what's left. And that what's left is this x minus 3 times x minus 6. So that goes on the other side. So it's just conversion, and I think I hopefully gave you enough converting problems so that you understand what I'm saying here about this. Now we just want to solve this equation. 4 to the first power is indeed 4. So I wrote down 4, copied it down. Now while we're at it, let's FOIL this. We've got 2 terms in here. Terms are added, and we could sneak a plus sign right in front of that minus sign and have adding a negative if we wanted to. Call it, we would have adding a negative there, which is fine. So we do have that, and we could sneak a plus sign in here too. And what I want to say is we want to FOIL because we have 2 terms here and 2 terms here because we can sneak in those plus signs. The only time you can use FOIL is if you've got 2 terms times 2 terms. So let's look at the first 2. X times x, that's x squared. The outer 2, x times negative 6, is negative 6x. The inner 2, negative 3 times x, is negative 3x. So we have negative 6x plus negative 3x, that's negative 9x. Last 2, minus times a minus is a plus. 3 times 6 is 18. So that's where we're at this moment. Feel free to ask questions if you don't understand a step. I want you to understand all the steps. So we need to solve for this. Now this is quadratic expression on this side. So let's get everything on one side. We can either factor or use the quadratic formula because all we have on this side is a constant. So let's move this 4. The opposite of adding is subtracting. Let's subtract 4 from both sides. That will leave us with a 0 on this side. And on this side, we will have x squared minus 9x right there. 18 minus 4 is plus 14. So we are looking for two numbers that multiply together to give us 1 times 14, which is 14, and add to give us -9. So let's write that down. So I've got to get this. So we're looking for two numbers that multiply to give us the outside. Let's look at, we're looking for two numbers that multiply to give us 1 times 14, 1 here, 14 here, 14. And add to give us this -9. Now I should mention this is, since we have a quadratic on this side set equal to 0, you're welcome to use the quadratic formula to solve this. You'll get the same answers if you do your math correctly. So 14 is 2 times 7. And we need to, and that is true, 2 times 7 equals 14, but 2 plus 7 equals +9, not -9. Well, the way to remedy that, and let me just put parentheses around here, at least the first one. The way to remedy that is to just change the sign on the 2 and to change the sign on the 7. So we get, if we do that, we get -2 times -7. And if we multiply, yeah, let me just try that again. Let's do this part again. I'm writing on my Max trackpad with my, oops, that I did not want to do. Let's see if we can figure out how to do this quickly. And I think we can. I've been using this for this semester. Oop, that didn't help. Let me see. Let's try one more time. And maybe I'll pick a different color or something just to kind of mix it up and change what's going on a little bit. So let's try this. So we've got a -2 times a -7. I may go a little bit over here, but that's okay. Okay? So -2 times -7 is +14. Now, if we add these two together, we get -2 plus -7. And that is -2 plus -7 is -9. So now we have two factors here and here. We put x in the first position in each, and then we're going to put -2 in one of them and -7 in the other. And we are going to take each factor, set it equal to 0, and solve for x. And what is going to happen with that, if we take x minus 7 and set it equal to 0, I think you can kind of see that just by looking at x minus 7 equals 0 here and ignoring what's over here. And all we would have to do is add 7 to both sides to get x by itself. So that will give us x equals 7. And I think you might even know that all you have to do is to get x is just change the sign on the 7. X equals +7. Here we would get x equals +2. Now remember, we need to check our numbers that we get and make sure all the arguments are positive. So we got x equals 7 and x equals 2. So let's go back up here and put in first, let's put in 7s up here for x. So we get 7 minus 3, which is 4, which is positive. That's good. That means that that still has the potential of actually being a solution. We want our arguments to be positive. Our argument is x minus 3, and in this case, it's 7 minus 3, which is 4, and that is indeed positive. Over here in this other argument, we put in 7 for x, and we get 7 minus 6, which is 1, which is also positive. So 7 is definitely a solution. So I circled it. Let's try 2. So I put the 2 down here so we're going to plug that in for x. We get 2 here for x minus 3, which is negative 1. Negative 1 is not positive. So we have to throw out this x equals 2. That is not a solution. So I crossed it out. It does not give a positive argument. Any questions on this particular topic? Now, this for some students is the most challenging of the topics on this test. That is the most challenging of the written work topics. Finding the time. Now you'll notice the time is in the exponent. And anytime we need to solve for a variable in the exponent, we really have 2 options. One is like bases equate the exponents, which in most cases is impossible to figure out how to do that. Although I could say it's theoretically possible. Maybe computers can do it, especially the computers have just become so advanced. But for practical purposes, you're probably not going to solve many equations that way where you get like bases and you equate the exponents. The only other way to solve a logarithm where you have a variable in the exponent is the only other way, I should say, to solve an exponential equation, because what we have here is an exponential equation where we have the variable t in the exponent. The only way to solve an exponential equation is either to get like bases equate the exponents or to take the logarithm of both sides. That's it. And really, the first option that I mentioned isn't going to work much of the time. So your only option is if you want to solve for a variable in the exponent like this n or this t, is to take the log of both sides. I did just copy this out of Alex. This will not be on the test here. You will need to know this formula right here. This A equals P times 1 plus R divided by N raised to the NT power. So let's read the problem and figure out what numbers are going where. Pablo deposited $2,000 into an account. That is the principal deposit. That is the deposit. That's the amount that was borrowed or deposited in the account. So that is our P. That $2,000 is going to go in for this P. With a 8.6% annual interest rate. So there are a couple of ways you can handle this. Note down here, this R is the annual interest rate, but it's been converted to a decimal. So you will need to convert your percent to a decimal in order to get the correct answer. There are a couple ways you can do this. You can ignore the percent sign, take the decimal point and move it 2 places to the left. So you would move it once to get 0.8, once again to get 0.086. So you would want to use 0.086, that decimal. The other way to do it, which is the way I like to do it because I always like to be as accurate as I can, is to remember that percent symbol means parts per hundredth. So we can take this 8.6 and then 8% is parts per hundredth. So we could then divide, that's supposed to be a 6, and divide by 100. So it's like this. Okay, so 100 here. I wasn't sure what that box was going to do. So we've got 100 here. And let me close this off and hopefully we can read that. So sorry for that little mark there. So if I do this on my calculator, 8.6 divided by 100, going to go to the home screen again, type in 8, decimal point down here, 0.6, and then division 100, 100, enter. And I get 0.086 over here to the right side. So let's go back. So we get 0.086. Either way, we're going to get 0.086. So this is equal to, let me see if I can get it to work for me. This is equal to 0.086. And let's make the decimal point a little more prominent there. Either way. So when we use this in our problem, we're going to want it to write it in as 0.086. So this 2,000 we determined was our P. So we could put P up here. This we determined we're going to is our R, it's our rate. And that's going to be equal to 0.086. Compounded semi-annually. So that would be down here, the number of times interest is compounded each year. Semi-annually means every 6 months, so that would be mean that the number of times that interest is paid per year is 2 times. So our N, that's why this N is 2 here. So wherever N is here, semi-annually, so this means N is 2. Assuming that no withdrawals are made, and actually you have to make an assumption that no more deposits are made as well, how long will it take for the investment to grow to $3,178? And that's our A. That's our final amount in dollars. So this is our A right here. So let's plug everything in, starting with the A. Let's go from left to right. Our A is $3,178. So I plug that in on this side. It's a lonely number. It's on this side by itself. Equals P. Our P is $2,000. Times, parenthesis, 1 plus R. R is 0.086. 0.086 divided by N. There's an N here and here. In both places, we want to put 2 in its place. So we want this denominator to be 2. And then we need a parenthesis. And this first factor in our exponent to be 2. And this T is unknown. Remember, we do want to find the T here. We want to, what we're trying to find is how long will it take for the investment to grow? How many years will it take? That's our t. So let's look at how we can solve this problem. We definitely have a variable in the exponent, so we're eventually going to take the logarithm, but we want to get everything away from this expression here that we can. So the first thing let's do, let's undo this multiplication by 2,000. The opposite of multiplying is dividing. Let's divide both sides by 2,000. Now you really want to be careful. There's a statement up here that says, do not round any intermediate computations and round your answer to the nearest hundredth. So they're saying, Alex is saying that you don't want to round until you get to the very end. And let me just show you something on the calculator. So how would you know if you, on your calculator, if you were rounding or not? That's a real important concept. So let's take a look at that. So what you could do, and I think I'm going to clear my home screen here because there's so much on it already. So I want to look for pi on the calculator. Pi is right here above the mountain peak. So I need, and that's in blue. So I want to use my second key first and then click on the mountain peak. And that puts a pi there. I wonder if I hit enter. So I hit enter and I get this. Now, pi is a non-terminating, non-repeating decimal. It goes on. Scientists for years have tried to figure out a pattern for pi, and there isn't one that they can figure out. So it's a non-terminating, non-repeating decimal. So you can try this on your calculator. And if what you get is less than all these digits, if what you get for whatever you're doing is less than all these digits, then you're safe and you're not rounding. You've got something exact, like if it stopped right here, for example. If you get too close, though, you might want to be careful because it depends what you've got out in front here too. So just be careful about that. But if you're only got 4 digits past the decimal point, you're probably okay. And you know, I've done that and I've always been okay. So I just want to show you that. So let's go back to our problem. So these 2,000s crossed out. On this side, we get 3178 divided by 2,000. So let's go do that on the calculator. 3178 divided by 2,000. And what do I get? 3178, and I'm just typing on my keyboard, computer keyboard, division 2,000. Enter. And I get 1.589. Now I compare that to pi. I know this is exact. It's nowhere near going out to all these digits. There's a lot of space between here and that 3. So 1.589. Wrote it down. And then I thought, well, it might be nice if I could figure that what's out in here and convince myself that is exact. So then you can I put 1 plus 0.086 over 2 in the calculator. So if I go back here and do that, I get 1 plus point bottom row 0.86 divided by, and that is 2. and enter. And I got 1.043. 1.043. So going back, I put that in here. And then we need to raise that to 2t. So we're down to something pretty simple looking. Notice we have a variable in the exponent, and all we have on the right side is a base of 1.043 to the power 2t. We need to get this t out of the exponent, and the only way we can do that is by taking the log of both sides. So let's take the log of this side and write that. And let's take the log of this side and write it as log of 1.043 raised to the 2t. And let's go to the next page. And I just copied down, right, this right here onto the next page. So I wrote down the power property for logarithms, and we've already looked at this earlier. Log base b of a base of the exponent, in this case, base of the exponent to a power. We have a property that says if the entire argument is a base to a power, which ours is, this entire argument here, over here, is this base to this power 2t. So we have just this entire argument can be viewed as a single base to a power. So we're good. So what can we do after we take the log of both sides? We are in this situation right here. And what this is telling us, that this side is equal to this side. And what we can do is drop this power down in front and then copy down this part right here before the power. So let's bring this power down in front, this 2t down in front like this. And what do we get? Copy this side down. This 2t is in the normal line of writing. And then we're just going to copy over log of 1.043. And we want to solve for t. Everything's on the normal line of writing now, except for the understood base 10s for these logs. So we want to solve for t. So I copied this side, I copied this down, copied this down, and we want to get t by itself. So this 2 is participating in multiplication with this t, so the opposite is division. So I want to divide both sides by 2. This log right here, log of 1.043, it's actually log base 10 of 1.043. That's one single real number being multiplied, participating in multiplication with that t. The opposite of multiplication is division, so we can divide both sides by log of 1.043 there and there. So the 2's cancel, the logs of 1.043 cancel, and on this side we're just left with this t, which I wrote on this side. And that equals what we have over here, log of 1.589 divided by 2 times log of 1.043. Now, when you put this into your calculator, you want to make sure anytime you have 2 or more numbers represented in numerator or denominator, you want to put parentheses around that numerator or denominator. This log, understood base 10 of this number, is a single number, so we don't need to do that. However, down here, this is 2 times this log. We've got 2 numbers represented, the number 2 and whatever this logarithm is equal to. So let's enter this into our calculator. So we have log of 1.589 over parenthesis 2 log of 1.043. So let's go ahead and enter that. So I'm going to go over here. Let's clear off the screen again. And this time we have log. LOG is right here in the first column. And that opens up a parenthesis for me. So then we put in 1.589 parenthesis, closing parenthesis. That didn't work on my keyboard, and I didn't realize it was going to take it all out of there. So I apologize for that. So I'm going to go back and get log again, 1.589, and I'll 1.589, 1.589, and then I'll use the parenthesis here, division, divided by, division symbol, parentheses. Got to put the whole denominator in parentheses. So we've got a parenthesis, 2 log LOG 1, and you notice a parenthesis was just automatically placed on the screen. 1.04, 1.04, and then a 3. Now I want to close off the argument, and I want to close off. I want to have another parenthesis that goes with this one that we opened with, and so I've got to put another closing parenthesis, and I'm going to hit enter now, and I get 5.9 or sorry 5.4999, which is what we got over here. What I got over here. It says in this problem to round to 2 decimal places. So we look at this digit. We have a 9. That's 2 decimal places. But the next digit is a 9, which is 5 or greater. So we have to add 1 to this 9. So I have 9 plus 1 here. So this works just like you learned arithmetic where you carry. You need to. 9 plus 1 is 10. So we write down the 0 and we carry the 1 over here and we get 1 plus 4, which is 5. So 5.50 years. Any questions on this particular problem? Let's go on. This one is finding the x-intercepts and the vertex of a parabola. Find the x-intercepts and the coordinates of the vertex. Remember, the vertex is the turning point. So parabolas either open up or down. So we want to find the coordinates of the vertex for the parabola. Our equation is y equals x squared minus 4x minus 12. If there is more than one x-intercept, separate them with commas. So let's find the vertex first. Now the quadratic formula is very interesting because it really has the how to find the vertex in it. So if I write out the quadratic formula here, we get that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. notice what's happening here. This part of the quadratic formula, right here, is the formula for finding the x-coordinate of the vertex of a parabola. To find the vertex, it's x equals negative b over 2a, which is precisely what we have here, x equals negative b over 2a. So we want to find the vertex of the parabola, the turning point. So our parabola either opens down or up. So we want to find our vertexes here or down here. So let's figure out, since we need to find the vertex and that involves the variables b and a, let's find a and b. Our equation's written in descending power order. So our a is the coefficient of the first term here, which is an understood 1. Our b is the coefficient of the second term here, which is negative 4. So our vertex is x equals negative b over 2a. We can see that from the quadratic formula. So that means that we have, this is equal to negative, our b is negative 4 over 2a is 1. Negative of a negative is a positive, 4 in the numerator. 2 times 1, which is 2 in the denominator. 4 divided by 2 is 2. So the x-coordinate of our vertex is 2. How do we get the y-coordinate? We just take our 2, plug it in for x. X is equal to 2. X equals 2. So we plug in our 2 for each of the x's and then find the corresponding y. So we're going to get y equals 2 squared. We're plugging 2 in for x, minus 4 times 2, minus this 12. So this is 2 squared, which is 4. So 2 squared is 4. Let's get us a little scratch area. 2 squared is 4. Minus 4 times 2 that's minus 8. And then we have minus 12. Right here. So what do we get? We get 4. And then we have negative 8 minus 12. That's negative 20. And 4 minus 20 is negative 16. So that makes sense. So our vertex is, our x-coordinate is 2, comma, our y-coordinate is negative 16. Any questions on finding the vertex? Let's look at finding x-intercepts. So if we want to find an x-intercept, what do we do? So let me just mark this up a little bit. Let me put a parabola here. Here's an x-intercept right there. How would we find that? That could be at, say, 2, 3, whatever. How would we find that? So what is the y-coordinate of any number on the x-axis? This is the x-axis. If I want the y-coordinate of any number on the x-axis, all that I have to do is trace it, that number, over to the origin to find out what its y-coordinate is. So for instance, I can trace this right here over, oops, we've got that phenomenon going on again, that mysterious phenomena. Let me try one more time. So if I want to know what the y coordinate is of this point, I can go right over to the origin there. Now this origin is 0, it has an ordered pair 0, 0. The x coordinate is 0 and the y coordinate is 0. What that means is any point on the x-axis, I can trace over to the origin and the y coordinate is 0. Any point, doesn't matter where it is. Every point on the x-axis has a y coordinate of 0. So we're going to start by letting y be equal to 0. And then we're going to solve for x. So we're going to go get our equation, which is right here, put in 0 for y. And then copy down this side right here, x squared minus 4x minus 12. And we want to factor that. So we're looking for two numbers that multiply to give us negative 12. And so this is multiply here, and add to give us this negative 4. So negative 6 times 2 is negative 12. Negative 6 plus 2 is negative 4. So that's what works here. So we can write down our factors x minus 6, x plus 2. If we set each factor equal to 0 and solve for x, we'll get x equals 6 and x equals negative 2. We just have to change the sign on the 6. Negative becomes positive here, and positive becomes negative here. So our x-intercepts are negative 2 and 6. Any questions on this particular topic? Let's go on. I think we've only got 2 more to go. Let's finding x and y intercepts given a polynomial function. Find all y-intercepts and x-intercepts of the graph of the function. So here we have a cubic written in descending power order, 3, 2, 1, constant. So the x-intercepts, as we just looked at, we find those by letting y be equal to 0. So we take out this y over here, replace it by 0. Copy this over. When we copy this over, we have minus 8 here, like that, but we can change that minus sign into adding a negative. A minus sign is adding a negative. They mean the same. And then what we want to do is pair off our terms. So we have 2 terms in each set of parentheses, and we want only a plus sign to show in the middle. And that's because there's 2 terms in here, and it's pretty common for students to get the sign of this wrong. So I think if you do it this way, you're much less likely to get it wrong. You want only a plus sign to show in the middle. So I just paired these up. I snuck in this plus sign here. We've got subtraction. Let's make it adding a negative, same thing. And that's so we can pair them off so that the plus sign shows in the middle and we're more likely to deal with this 40 correctly. So got them paired off. This 10 I wrote as 2 times 5. And so the first step here is let's go ahead and factor out a 2 because we have a 2 here and here. I didn't want to cross too many things out. I wanted you to be able to see. And we've got 3 x's here and 2 x's here. So we have 2 x's in both terms. So let's take this 2 out front and an x squared out, 2 of the x's out. And what do we have left? This 2 went out front. 2 of these x's went out front, but 1 is left. So 1 goes inside. Minus, We were ignoring the 10. It got changed to 2 times 5. The 2 went out front. We're left with the 5. And this x squared, all of that x squared went out front. Plus, now, when you want to look at this, we need to do something with this negative here because we're not going to get matching factors here like this if we don't. And so let's factor the negative sign out. When you factor a negative sign out in front, it changes the signs inside, changes all the signs inside. They become the opposite. So we're going to factor this negative out in front. That means inside this, the sign is going to be opposite for this term. It was negative. It's now going to be positive 8x. It was positive inside. When you factor this negative out, it was positive inside. Because the negative sign went out front, it is now the opposite, which is minus 40. 40 we can factor into 8 times 5. So we got this far. So this time we're just copying all of this down here. And now we want to factor an 8 out. So let's take an 8 out of the first term here. So this 8 went out all the way out front. And we have an x left inside minus this 40. Let's ignore it. It was replaced by 8 times 5. So the 8 went out front and we're just left with the 5 here. So we have x minus 5 here. So right now we are wanting to factor out of terms. Terms are added. I could sneak a plus sign in here. This term has an x minus 5 in it. This term has an x minus 5 in it. So we're going to factor that x minus 5 all the way out front. And we have equals 0 on this side. If we take this x minus 5 out, we have 2x squared left minus this one out front. So all we have left is a minus 8 inside. So in order to figure out what our x-intercepts are, we need to set each one of these factors equal to 0 and solve for x. Let's do that. So x minus 5 equals 0. We're going to move the minus 5 to the other side. We'll end up on the other side is plus 5. 0 plus 5 is 5. So x equals 5. This one, you could factor it more if you wanted to, or you could work with it with the x squared in it. There's no middle term of x, so it's pretty easy to work with. You could add the 8. So the opposite of subtracting 8 is adding 8 to both sides. These cancel because we get 0, and 0 plus what's left is what's left. So we get 2x squared equals 0 plus 8, which is 8. Now we could divide by 2. We're trying to get everything away from the x squared. Opposite of multiplication is division. So let's divide both sides by 2. These cancel. They give us 1 times x squared, which is x squared, equals 8 divided by 2, which is 4. So now if we take plus or minus the square root of both sides, we're going to get plus or minus 2. So our x-intercepts are 5 plus 2 minus 2. And Alex wants us to separate them with a comma. I should mention that since our originally function is a cubic, you're likely going to see 3 different x-intercepts because of that. Any questions on finding the x-intercepts? Finding the y-intercept, there's only one. Otherwise, the graph won't pass the vertical line test. So how do we find it? When we find, just like when we find an x-intercept, we let the opposite coordinate be 0. That's what we do here. When we want to find a y-intercept, the opposite coordinate, which is x, is 0. So we're going to put 0 in here, here for x, and here for x. 0 cubed, that's 0 times 0 times 0 is 0 times 2 is 0. minus 10 times 0 squared, which is 0 times 0, which is 0 times 10 is 0. So we got 0 for the first two terms, minus 8 times, we're putting in 0 for x, and 8 times 0 is 0. Now we got 0 for the first three terms, and if we add them all together, treating subtraction as adding a negative, we're still going to get 0. And all we're left with is this 40. And the y, so the y-intercept is 40. And that's it. So any questions on this particular topic? And this is our last topic that we are going to take a look at. Using a given 0 to write a polynomial as a product of linear factors, real zeros. So what we want to do is use synthetic division. You can use long division if you want to. I'm going to present with synthetic division. So the 0 here, -3, goes out in front of the synthetic division table up here. And then we want to make sure we include every term here. If you're missing a term, you need to put in 0 for a placeholder. So we have 3, 2, this is an understood 1, and a constant is degree 0. So we have them all. So the coefficient of x cubed is 1. The coefficient of x squared is 9. The coefficient of x is 25, and the constant is 21. Luckily, those are all positive. If there were some minuses in there, you would have to include the negative signs. So let's go ahead and perform the synthetic division. So whatever this first number is, it just gets dropped straight down. Drop it down. And then we take this number and multiply it by this number down here. -3 times 1 is -3, and that number goes right there. We then add straight down. 9 plus -3 is 6. We then involve this number and take -3 times 6 to get -18. We add 25 minus 18 is 7. We take this number -3, multiply it by the 7 to get -21. 21 minus 21 is 0. And since we were told that -3 is a 0, this is our x, this is our y down here. That's an ordered pair on the graph, actually. And we get -3 for x, 0 for y. And you want to get, that's the definition of a 0. It's an x coordinate that makes y 0. So if you don't get 0 here, you've done something wrong, because we know that -3 is a 0. So now what do we have? If you notice what we have here, this was a cubic. We did a division, although we turned it into addition, but we really did a division here. And with the degree goes down by 1 when each division that you do. So we started it with an exponent of 3. That exponent reduces by 1 to 2 right now. So we have right here, this 0 you ignore. Okay, that's just verifying we have that -3 is a 0. Right here, you've got a constant, you've got an x term, and you've got an x squared term. So what you have here is a constant, you've got an x term here, and you've got an x squared term here. If you write those back in. So we really have a quadratic equation. That's really what we have. So to find our other two zeros here, we can set this right here equal to 0 and solve for x. So we can use the quadratic formula, and this is this one here is our A. This 1 is our A. This 6 is our B. This 7 is our C. We already know what those, our A, B, and C are automatically. So quadratic formula, x equals negative b, that's 6, plus or minus square root b, which is 6, squared, minus 4, a is 1, and then the c here is 7, and that 7 goes in. All over 2a, a is 1. So I like to work with the square root first. Let's look inside the square root here. 6 squared is 36. Minus 4 times 7 is 28. So minus 28. So 36 minus 28 is 8. So we're looking at square root of 8 here. Now 8 we can break down into 4 times 2. Square root of 4 is 2. So this 8 is 4 times 2. This 2, the square root of 2 stays because we can't break that down anymore. So we get square root of 4 is 2. The square root of 2 stays. So we get 2 square root of 2. So now we have negative 6 plus or minus 2 square root of 2 over 2. And we spend a lot of time in college algebra on factoring. You can cancel factors, but you cannot cancel terms. We can't cancel those 2's. And it does not work like that. So you want to factor out of the numerator. So this negative 6 here is really 2 times negative 3. So we can write this negative 6 is 2 times negative 3. And we can cross this out if you'd like. And now that's what we have. So we can factor out, we've got a 2 here. We have a 2 in this term here. Terms are added. Subtraction is just adding a negative, so you can consider subtraction as being terms. So we have in this term we have a 2, and in this term we have a 2. So we can factor that 2 way out front, right there. If we do that, then we're going to, this 2 went out front. This 2 went out front. Oh, it's like, let me think I've got to switch colors or do something and mix it up on. This 2 went out front. This 2 went out front. So we are left with negative, we've got this 2 out front. We're left with negative 3 here, plus or minus square root of 2. That's what we're left with. Divided by 2. 2 divided by 2 is 1. 1 times what's left is what's left. And what's left is negative 3 plus or minus the square root of 2. So our zeros are, we found 3 zeros here. Let's look at what they are. Our zeros are the given 0, which is negative 3. And let's make sure we understand, yes, we want to express h of x as a product of linear factors. So this tells us we have 3 linear factors. So we need to use all of them. So our zeros are these 2 and negative 3. And we want to write the factors. So if you have a 0, x minus that 0, x minus that 0 is a factor. So we have x, our first 0, let's use the given 0, x minus a 0 is a factor, so x minus from here, and then this negative 3. So we have x minus a negative 3 minus a minus is a plus. We actually have x plus 3. And then here, parentheses x minus, we have negative 3 plus square root of 2. We'll choose the plus one. Negative 3 plus square root of 2. That's 0. This 0 here, because it had this 0 here, negative 3 plus square root of 2 has two terms. We're going to put that in parentheses because of that. So this set of parentheses is for the 0. This set of parentheses is for the factor, the outer set. And this part here is just x minus the 0 is right here in parentheses. Let's use x minus 0 again. So this time we want to have parentheses x minus, and we're going to put the 0 in parentheses, just like we did before. This time our 0 is negative 3 minus square root of 2. Negative 3 minus square root of 2 in parentheses. So again, you want the 0 in parentheses, and then the entire factor in parentheses. Any questions on this particular topic? So that's it, but I will come up there and ask you, Carrie, do you have any questions of any kind?
No, not on this stuff. No. I am struggling. I there's so many rules to the logarithm, so I forget which property to use at each time. So I'm going over and reviewing all of that this week, so I'm ready.
So do you plan on doing the test 3 review no credit assignment?
Yes, I'm working my way through that right now.
That's a great assignment.
I think there's like maybe 9 or 10 problems left that I'm still working through.
If there's a particular problem you would like me to go over with you, I can do that.
I think so far I'm doing okay. But like I said, the logarithms is kind of like where I'm struggling the most at the moment, just because I forgot